Okay, so exercise 6.3. I'll explain this just with the diagrams in the yellow box might be best. I've got a point P and I'm interested in the instantaneous rate of change at that point. So I know what I could do is graphically place on a tangent line and then calculate the gradient of that tangent line. But let's now consider this. I've got that point P and it occurs at some x value. If I now take another point to the left-hand side of that and go out a horizontal distance of h, this x value is going to be x minus h because I'm going to the left, going backwards. If I then go up to the curve, I'm going to get this point Q. What I can do now is calculate the gradient of that secant that joins the lines, that joins the points Q and P. And the gradient of this line here is going to be approximately the same as the gradient of the tangent line at point P. Therefore, I can say that the gradient of this line is approximately the same as the instantaneous rate of change at point P. That's the background behind it. So how do I calculate the gradient in this line here? It's going to be the change in y over the change in x. So here's the calculation. Change in y over change of x. So remember this is point, this here at Q is x1, y1, and this here is x2, y2. So what I want to see is y2 take y1 over x2 take x1. I can also describe this point here as being x comma f of x. I can describe this point here as being x minus h comma f of x minus h, and that's shown here on the sides. So my rate of change, or my instantaneous rate of change, is approximately going to be equal to this. I'm going to have f of x minus f of x minus h over x minus x minus h. Now, what that will simplify to become is just h, so it's over h. So this is incorrect. That should be an h down the bottom. I can also apply the same idea looking at moving a point to the right. So again, here I've got point P. I'm interested in working out the instantaneous rate of change at point P. So of course I could draw on a tangent line and calculate the gradient of that tangent line. But what I can also do is say, okay, here's x. Let's now look at a point that's a little bit across to the right hand side. Let's move a horizontal distance of h units across. So I'll get x plus h. Look at where that is on the curve. So here's point Q. Again, I know that if I can calculate the gradient of that secant, it's going to be approximately the same as the gradient of the tangent line. So therefore, the gradient of this secant is going to be approximately the same, is going to be approximately equal to the instantaneous rate of change at point P. So how do I calculate the gradient of this line here? It's going to be y2 take y1 over x2 take x1. So my calculation will be this. Change in y over change of x is going to be f of x plus h minus f of x. So f of x plus h minus f of x over x plus h minus x, which would of course be h. So these are my two rules that I have, whether I'm using it from the left or to the right. Let's look at an application. Find the approximate rate of change for f of x given this cubic between the x values where x is equal to 2 and x is equal to 2.1. Approaching x equaling 2, so that's where I'm interested in, from the right. So what we've got going on here is this situation. So we're from the right, we've got x equaling 2 and x equaling 2.1. The horizontal distance is 0.1 obviously, and I can have my points P and Q, do my calculation based on this to get an approximate answer for the rate of change. So x equals 2, the x plus h, the point to the right hand side of it, is 2.1, so that means the difference between the two, the horizontal distance, is 0.1. I now evaluate what f of 2 is, so I sub 2 into the function to get 11. I sub 2.1 into the function to get 12.051. So my rate of change in y over change of x, I use this rule here because it's to the right and it's specified in the question. So it's that version of the yellow box that I use, and I sub everything in and I end up with 10.51. So the approximate rate of change is 10.51. Problem 2. We're told that the horizontal distance is 0.2. We need to find the approximate rate of change for this function at x equaling 3, and we're approaching from the left-hand side this time. So what we've got going on here, folks, is this situation. Okay, we've got 3, x equaling 3, and then the point on the left-hand side is 0.2 units across. So here would be 2.8, and then obviously I can work out the y values and then calculate the gradient of that line joining it, which will give me the approximate instantaneous rate of change at point P here. So let's look at the calculations for it for problem 2. Sorry for scrolling all over the place. So x equals 3, we're told the horizontal distance is 0.2, and we're doing it from the left, so it's x minus h. 3 take away 0.2 gives me that 2.8. F of 3 is 43, F of 2.8 is 37.4. My rate of change is approximately going to be equal to this. So it's that version of the rule that I'm using in the yellow box. So it's 43 take 37.4 over 0.2 to give me 28. So my approximate rate of change is 28. Here we're going to be looking at this idea of a gradient function. Let's consider the graph y equaling x squared. You can see that it's a curve. So therefore, it's not a constant rate, it's a variable rate. We know that we can calculate the instantaneous rate of change at any point on the curve. And we can do that by simply drawing on a perfect tangent line and then calculating the gradient of that tangent line. You can see that as x increases, the steepness of that blue curve is increasing. And therefore, the instantaneous rate of change is also increasing. And that's shown even more so by drawing on the tangent lines here. You can see that they're clearly getting steeper, those tangent lines. It would be possible for us to generate a table of values. So if we've got x for 1, 2, 3, and 4, if we then went back to the original graph and looked at the gradient of each of these tangent lines, the instantaneous rate of change, that's a change in y over change of x, you'd be able to see from the graph that when x is equal to 1, the instantaneous rate of change is 2. When x equals 2, the instantaneous rate of change is 4, and so on. So from that, it's very easy for us to recognize a pattern. What we can see here is that the gradient is going to equal 2 times whatever x is. So if x equaled 10, then the gradient, the steepness of the curve, or the instantaneous rate of change, would be 2 times 10 to give me 20. And that's quite handy. This is known as the gradient function. And that's shown over here on the right-hand side. So change in y over change of x, that's the gradient. That's x changing. So it can be seen that as x increases, the steepness of this original graph increases, and it's shown here. And it's this format, y equaling 2x. Okay, that's the equation for the gradient function. And this is quite handy. So that just means that I don't need to draw tangent lines. I already know what the rule is. So give me any value of x, and I just multiply that by 2, and that will tell me the instantaneous rate of change at that point. So as an example, that's x equaling 1, this is x equaling 2, that's x equaling 3, and I've got those particular values below in that yellow table. But for 2.5, x equaling 2.5, well, what I know is that the gradient is going to be 2 times whatever x is. So at this particular point here, where x is equal to 2, I know that the instantaneous rate of change here is going to be equal to 5, 2 times 2.5. And this is what we refer to as being the gradient function. Okay, another problem. Use h equaling 0.1 to find the gradient function r of x for this function here, f of x. So that's r of x, that's going to be the gradient function. We've got f of x equaling x squared plus x for x values of 1, 2, and 3. And we're approaching each value from the right. So here's the background, guys. The gradient of the curve is going to equal the gradient of the tangent line, which is equal to the instantaneous rate of change, and that's equal to the gradient of the secant of the points that are close on the curve. So that's that idea of of x and x plus h, where the horizontal distance between the two is very close. So the gradient of the secant is going to be approximately equal to the gradient of the curve. Let's consider for x equaling 1, the gradient of the curve using the right rule, okay, because we're told to approach it from the right, is f of x plus h minus f of x over h. We are told in the question to make a horizontal distance of 0.1, so it's f of 1.1 minus f of 1 equal over 0.1 to give me 3.1. So what I can see here is that the gradient of the curve is approximately equal to 3.1. So given I've used 0.1 here, I make the assumption that if x equals 1, the gradient equals 3. Let's now investigate x equaling 2. Gradient of the curve will be approximately equal to 5.1. Again, using this rule, substituting x equaling 2. So that's f of x plus h, so x equaling 2, so the horizontal distance across is 0.1, so f of x plus h, so it's f of 2.1 there, over 0.1, so it's approximately equal to 5.1, so I make the assumption that when x is equal to 2, the gradient is equal to 5. X equaling 3. The gradient of the curve is approximately going to be equal to 7.1. This is f of x plus h minus f of x over h. So when x is equal to 3, the gradient is equal to 7. So now if I put that in a table of values, here's x, 1, 2, 3. Here's the gradient, which I'm referring to as r of x, and that's 3, 5, 7. It becomes pretty easy for us to notice a pattern. And it's this. I'm jumping up by 2 each time, so I know it's linear, and I know that the gradient is equal to 2. And what I also know is that I need to add 1 to it. So in order for me to establish the gradient, I multiply the x value by 2 and add 1. It's a very easy pattern for me to establish. So this is known as the gradient function. So r of x is equal to 2x plus 1. So what does it tell me? So if I've got this curve, f of x equaling x squared plus x, in order for me to work out the instantaneous rate of change for any x value, I just get that x value, multiply it by 2 and add 1 to it. Again, we've got some complicated CAS explanations here. I wouldn't touch that at all, guys. It's only going to mess you around. So ignore that, please.